Today, let's talk about the biggest mystery in physics, the measurement problem. The title is Where is the Hand of God?
That's a pretty grand title. Nice to meet you.
Physics is amazing. In the 19th century, it really felt like we had already uncovered everything about the world.
Yeah. With Newtonian mechanics and Maxwell's equations, people thought nature could be explained completely.
But then we learned that light can behave like particles, and electrons can have wave-like properties, and everything fell into chaos.
Is it a wave? Is it a particle? It makes you want to yell, which is it?
So then came the Schrödinger equation, built on wave behavior, and matrix mechanics, which can handle particle-like behavior.
They look totally different, both the equations and the style. Why are there two?
That's the key point. Later, von Neumann proved that these two are merely different perspectives on the same underlying entity, the state vector.
So even if the formulas and calculation methods look different, the state vector, the true form of the universe, is one and the same.
Exactly. And that state vector evolves beautifully and deterministically, until we observe it.
There it is, the measurement problem. The Copenhagen interpretation: the wave collapses the instant you observe it.
Right. Mathematically it should evolve smoothly, yet only at the moment of observation an abrupt, discontinuous change called collapse occurs. It's far too artificial and unnatural.
So that's why the many worlds interpretation appeared, right? The idea that the world splits every time we observe.
The idea that both the world where you did your homework and the world where you didn't exist. But even if you reject the artificial operation of collapse and choose many worlds, you end up introducing another equally outrageous artificial operation, branching of worlds.
So whether it's collapsing or splitting, it's the same kind of thing, rules humans decided on arbitrarily.
Exactly. If the Copenhagen interpretation is incomplete, then the many worlds interpretation is also incomplete. And every time an observation happens in this universe, worlds branch without limit. How many worlds would that create? It's beyond imagination.
Then what about decoherence theory? The idea that information leaks into the external environment we can't perceive, so it looks probabilistic to us.
If we knew the universe's complete information, we could predict the future state deterministically. In other words, God does not play dice. But because our information is incomplete, it looks like the state collapse is probabilistically right. From set theory, we can logically prove that a subset cannot possess complete information about the whole set. So the assumption of decoherence theory, the information we have is incomplete, is logically correct as well. What's interesting here is the contrast with thermodynamics. In thermodynamics, we fix the state of the environment and then define free energy. In other words, it presupposes information about the entire universe including the environment.
I see. By fixing the environment, free energy contains the full information.
But in quantum theory, we can't know the environment completely. So information leaks into the environment, and as a result the measurement problem and an apparent collapse arise.
So thermodynamics assumes complete information including the environment, while quantum theory assumes the environment is unknown, so information leaks. That's a fascinating contrast.
But with this way of thinking, we end up falling into an anthropic view. The world looks probabilistic because the observer lacks information.
It would be strange if the laws of physics changed depending on whether I look or not. Isn't there a more objective reason?
So one promising idea is a model where the destination of the lost information is sought in higher dimensional space or other universes.
Higher dimensions. That suddenly sounds kind of occult.
No, it's cutting-edge quantum gravity. For example, M-theory predicts that this world is 11-dimensional.
11 dimensions. I thought we lived in 4, length, width, height, and time.
The remaining 7 dimensions are said to be tightly compactified, or in a domain we can't perceive. When information seems to disappear in quantum mechanics, it may be because it is leaking into those higher dimensions beyond our cognition. There is also a multiverse model where universes other than ours exist. This is not the branching worlds of the many worlds interpretation, rather, it is the idea that events like the Big Bang may occur elsewhere too, and many universes might exist. If so, there could be a possibility that information leaks from our universe into other universes as well. This information leak also reaches into the very foundations of thermodynamics.
Thermodynamics? Like engines.
Entropy. Entropy can be rephrased as the degree of missing information. If information keeps leaking from this universe into higher dimensions, the amount of information in our world decreases, and entropy keeps increasing.
That's exactly the second law of thermodynamics, the law of increasing entropy.
Moreover, in many-body quantum mechanics, the thermalization hypothesis allows us to derive the second law from missing information. It overlaps with decoherence theory in many ways. Even more important is that, in quantum mechanics, statistical behavior appears through the time evolution operator exp, beta h. It has the same mathematical form as the Boltzmann factor in statistical mechanics, but it doesn't use statistical mechanics. In statistical mechanics, we treat the Boltzmann factor as a probability and handle ensemble averages.
So quantum time evolution and ensemble averages in statistical mechanics share the same structure.
Exactly. And in systems where the two coincide, the ergodic hypothesis follows naturally. That is a basic postulate of statistical mechanics, and quantum theory supports it as well.
I see. Quantum time evolution connects to statistical averages and even guarantees ergodicity that really feels like the seed of a unified theory. So the information leak in quantum theory and the increase of entropy in thermodynamics have the same structure.
Yes. The flow of time from past to future, a room becoming messy, quantum probabilities, everything might be explained by a single phenomenon, information leaking into higher dimensions.
Amazing. Quantum theory and the measurement problem, information theory, and thermodynamics all connected through an 11-dimensional world.
Up to this point, we've said that the time evolution of the state vector of the entire universe is deterministic. Measurement is the result of projecting the state vector at that moment onto the measurement system. The projected partial state contains many possible measurement outcomes.
What the observer actually experiences is just one of them.
Exactly. In the end, even with this understanding, the measurement problem cannot be avoided. But the observed result is only the observer's experience, and it does not affect the state vector of the entire universe. The outcome of an observation does not change the future.
That's the part people have been misunderstanding about the measurement problem.
Decoherence theory has made several questions in quantum mechanics much clearer.
But the universe is still full of mysteries.